Okay, so welcome to the set theory seminar. It's my pleasure to introduce Corey Switzer, a very familiar face in New York, who is currently in Vienna. And he's going to talk about tight, maximal, eventually different families.
All right, great. Thank you all so much for coming, and thanks for having me. It's really great to be here, virtually, even after having been gone for not very long. Always nice to come back. So today I'm going to talk about tight, maximal, eventually different families, whatever those are. Does this work? Yeah, okay, cool. So this is joint work with Farah Fisher. All right, so what I essentially want to talk about are sort of maximal sets of reals in the sense that I'll make precise. And so I'm going to be talking about MAD families, which are probably fairly well known to people here, and also their relatives, particularly something called maximal eventually different families. And on this note of having just copy and pasted random things, I wanted to give you an idea of what a MAD family is. So that's a MAD family. That's actually just me with my parents during quarantine. My hair grew back when I moved to Vienna. And then here's an eventually different family. Not me. Anyway, more concretely, just recall the following. So we're going to be working oftentimes in this, what I sometimes call the Ramsey space. It's the set of infinite subsets of omega. And so if I have two of those A and B, then we say that they're almost disjoint if their intersection is finite. More generally, almost anything means mod finite usually. And so a family of sets is almost disjoint if it's pairwise, all of its elements are. And such a family is MAD, or maximal almost disjoint, if it's maximal as an almost disjoint family with respect to inclusion, right? It's not included in any larger almost disjoint family. And you can always kind of easily generate finite MAD families, but they're boring. So we always mean an infinite MAD family, at least in this talk. And so, like I said, MAD families are this kind of prototypical example of a maximal set of reals, which I'll give you some other examples in a moment. But first, I want to kind of set the stage a little bit. And so when we talk about MAD families, when we talk about any kind of maximal set of reals like this, there's kind of two main questions that we're thinking about. So the first one I call the combinatorial question. And so this is just sort of what are the possible sizes of a MAD family? And in particular, what is the least size of a MAD family? And so we get this well-known cardinal characteristic A, which has been studied since at least the 70s. For example, Heckler proved that you can have A be any regular lambda less than or equal to the continuum. And you can even have A be singular and even equal to aleph omega. So that was proved by Jörg Brendle, like maybe 15 years ago. And for this talk, also I want to highlight a kind of ZFC result that's going to be useful to us that I couldn't find a reference on, and it's kind of well known. Maybe it's just folklore, but the bounding number B is less than or equal to A in ZFC. All right, and then the second question we can ask is what I call the descriptive question. Right, so what are the possible definitional complexities of a MAD family in the sense of descriptive set theory? So obviously, the way you know that MAD families exist is, well, you have an infinite almost disjoint family, and then you apply Zorn's lemma. And there's a sort of natural question is, could you build one sort of by hand? Without appealing to the axiom of choice? And the answer is no, and you can see this in sort of a variety of ways. So the first theorem is a very famous one due to Matthias, that there are no analytic MAD families. So that space, square brackets omega to the omega, I can think of it as a Polish space, and I can talk about, the sort of complexity, Brel and projective complexity there, and there are no analytic MAD families in that sense. And in fact, there's no MAD families at all in the Solovay model. So Matthias proved that, so if you don't know what the Solovay model is, it's a choiceless model of set theory that's constructed from an inaccessible. And so Matthias proved that if that inaccessible happens to be Malo, then there's no MAD families. And Turnquist reduced that to just the inaccessible. And then the kind of, the best result in this sort of vein is that if AD holds an L of R, then there's no MAD families at all in L of R. So that was proved independently by Niemann and Norwood and by Haga, Schrödinger, and Turnquist. And so these are kind of all negative results, and a lot of them have to do with kind of large cardinals. But on the positive side, if V equals L, which you can obviously think of as a kind of anti-large cardinal property, then there's a pi-1,1 mad family. And that was shown by Arnie Miller. And I'm going to talk about that result actually in the second half of my talk. Let me also just say, I realized I forgot to say it. If it wasn't clear, please feel free to stop me and interrupt and interject at any moment. I like that. In any case, so, this context of almost disjointness, I want to talk about these relatives, and the way we get relatives is we can insist that we don't just have sets that are almost disjoint, but these sets have some extra structure on them, or the family of sets might have some extra structure on them. And that's what I really want to kind of focus on today. And so before I can do that, let me just give one more definition. So recall that if I have two functions f and g from omega to omega, then these functions are said to be eventually different, which I write as f not equal star g, just in case for all but finitely many k, f of k is not equal to g of k. And let me just note for later that the negation of eventual difference is infinitely often equal. So there are infinitely many k, so that f of k equals g of k, which I write as f equals infinity g. And now a family of functions will be eventually different, again, if its elements are pairwise, like with almost disjointness. And such a family is a med family or a maximal eventually different family if it's maximal with this respect. So note that if I have two functions which are eventually different, then if I think of them as a subset, each of them as a subset of omega squared, they're almost disjoint in the sense that I gave you before. All right, so given this, I want to just list some sort of relatives of almost disjointness that I'm going to talk about today. So these eventually different families, and we get this cardinal characteristic A sub E, which I'm going to talk about a lot. It's not equal to A, and we'll see that. And unlike mad families, though, actually there's a Borel maximal eventually different family, and that was proved by Horowitz and Shellock. And in fact, there's actually a closed one that was proved by David Schredisser. And then I can do the same thing, but I can restrict my attention to permutations. So S of omega is a set of permutations of omega. And we get this cardinal characteristic A sub P, and again, there's a Borel maximal eventually different family of permutations. The next one I want to talk about is if I look at almost disjoint sets of finitely branching trees on omega. And I get this cardinal characteristic again, A sub T, and this actually is equivalent to the least size of a partition of bare space into compact sets. So that was proved by Miller. And there's also a Borel maximal almost disjoint family of finitely branching trees. When I was writing this talk, I realized I had never read anything about definability for these. And then I realized that the reason why is because it's obvious. Unlike those two other theorems about there being Borel med families that are quite difficult, this just follows if you take for each element of bare space, you look at the tree of initial segments, and that gives you a Borel family of finitely branching trees in a kind of trivial way that are almost disjoint and maximal. And then the last one, which I'm not totally going to talk about.
Corey,
yes.
Could I just ask? Could you explain what do you mean exactly by finitely branching trees? Are these supposed to be finite objects, or?
No, sorry. I mean trees consisting of sequences of elements of omega.
Okay.
So that given any node, it has only finitely many 6 others.
Oh, I see. Finite splitting. I see. I get it.
Sorry, yes. Finitely splitting trees would maybe be better.
I see. Okay, I somehow misunderstood. I thought you meant that there are only finitely many points at all that where it splits.
Yeah, no,
okay,
yeah,
okay,
no,
okay. I see. Okay, no, thank you.
Yeah. Okay. Yeah. Right. Yeah. The compact subsets of bare space are exactly the branches through finite splitting trees, and that's where this characterization comes from. And so the last one I want to talk about are maximal cofinatory groups. So if I think about my family of eventually different permutations, but I want to look at maximal subgroups of S of omega that are eventually pairwise eventually different. We call this a cofinatory group because since I have the identity, every other element must be eventually not, it must not have infinitely many fixed points. Otherwise, it would be infinitely often equal to the identity. And so I can look at the sort of least size of a maximal cofinatory group. Again, I get this cardinal characteristic AG, and again, Horowitz and Shellock proved that there's a Borel maximal cofinatory group. Okay, so sort of taken all together, we get these 5 cardinal characteristics relating to these 5 notions of almost disjointness, including the standard one. The descriptive question is what I'm going to talk about in the second half of my talk. But right now I want to sort of focus on this combinatorial question, these cardinals. So these 5 cardinals, they all seem extremely similar to one another. We don't know that much about how they relate. And in general, just even on their own, they're kind of mysterious. Even A, despite this fact that we've sort of studied them intensely, there are some kind of basic open questions still. And just to give you kind of an example of how little we know, here's a list of all of the known ZFC implications between these 5 numbers that look kind of the same. Okay, so this is an even worse joke than my picture of George Costanza. This isn't where I click next and there's a list on the slide. This is the list. That's all we know, nothing. And similarly, I could just ask, well, are there any kind of upper bounds, cardinal characteristics that we know are going to be provably greater than any of these numbers? Well, obviously the continuum, and then same joke, that's the list. So there's some very mysterious things. I might mention in this regard, a very sort of interesting, prominent open question is I, the independence number, provably an upper bound on A? That's a very good candidate, and we don't know if that's true or not. Okay, but sort of joking aside, what we actually know is the following. So I told you before that B is less than or equal to A. Now the uniformity of the meager ideal, which I write non-M, so the least size of a set of reals which is not meager, is a lower bound for all 3 of my almost disjointness numbers that come from functions. So AE, AP, and AG. That was proved by Brenla. And Otmar-Spinas proved that AT is less than or equal to D, the dominating number. And then finally, AT is independent from these 3 function numbers. So independent, I mean, it's consistent that AT is larger than all of them, and it's consistent that they're larger than AT. This was known, but I don't know if it was ever written down before my paper with Vera. It follows basically from these, plus the fact that Kuhnen and independently Stern showed that it's consistent that AT is strictly less than the uniformity of the meager ideal. And conversely, Castermans and Zhang proved that it's consistent that these 3 numbers are less than D. So when you put together 2 and 3 with those facts, you get this independence. And just something to note is that B is provably less than or equal to D and the uniformity of the meager ideal. So B is a lower bound on all of these cardinals. However, A, D, and the uniformity of the meager ideal are all pairwise independent. So that, for example, tells you that A is not equal to any of the other 4. Because, for example, we know that A can be strictly less than the uniformity of the meager ideal, and hence strictly less than those 3. And the same thing with D. And it's every model where we've computed them, we know that A is either less than or equal to all of the other 4. And Jörg Brenla has conjectured that actually this is provable in ZFC, but we don't know how to prove it for any of the 4 of them. So there's kind of a lot of open questions. And then the kind of most embarrassing one is that actually these 3 function numbers, AE, AP, and AG, we have no idea how to separate them or if they're equal. They seem extremely similar, particularly AE and AP, and yet we don't know how to prove even one inequality between them. So, I mean, I feel like they must be the same, but I have no idea how to show that. So it's, I think, an even more basic question that we don't know how to solve. So this is kind of what we've been thinking about. I mean, what I've been working on since I came to Vienna is just trying to understand these questions. And if you want to start to tackle these questions, the way that you do it, or like at least a kind of natural way to start to think about it, is you want to consider special witnesses, special maximal eventually different families, special mad families that are going to kind of play nicely with forcing, so that you can maybe try to get a consistency result. And the results we do have kind of are along these lines in general. And the most natural form that you might try to take this is by looking at some way that you might strengthen the maximality condition so that a given family is going to stay maximal in whatever its sense of maximality is in a forcing extension, right? It's going to sort of be maximal in a sense that can't be killed by a specifically chosen forcing. And in the case of madness, this line of inquiry is well established. I think like 3 or 4 weeks ago, Michael Hrushek at the Toronto seminar gave this really great talk about different types of mad families and mentioned a lot of these things. And in particular, he talked about a particular example that I want to focus on today, which is called tightness. So in an infinite almost disjoint family A, the ideal generated by A is just the set of B, which are almost covered by finitely many elements from A. And A is tight if anytime I take a countable set, Cn of I of A positive sets. So a countable set of elements, each of which cannot be almost covered by finitely many things from A. Then there's a single B, which has infinite intersection with all of them. Sorry, a single B in the ideal. So if you want to think of maximality as being kind of one-to-one, for every set not in A, I can find something in A which has infinite intersection with it. This is a sort of strengthening that's kind of countable to finite. Given any countably sets that are not in A, I can find finitely many things in A that have infinite intersection with them. So it strengthens maximality. And it turns out that it's going to kind of play nicely with forcing. Tight mad families exist if B, the bounding number, equals C. So in particular, they exist under CH. This B equals Z result is due to Hrushek and Ferreira. It's a sort of important and interesting open question if it's consistent that there are no tight mad families. We don't know. But sort of assuming that they exist, and since we oftentimes work in a ground model of CH, we can assume they exist for forcing arguments. They have these kind of nice properties. So for example, their tight mad families are Cohen indestructible. So that means that if I add any number of Cohen reals, then they remain maximal in that extension. And that was proved also by Hrushek and Ferreira. And more interestingly, and this is kind of the theorem that Vera showed me when I got to Vienna, and this is sort of the jumping off point for what we ended up doing. If A is tight, and I take a countable support iteration of proper forcing notions, so that at each stage alpha, Q dot sub alpha is forced to strongly preserve the tightness of A check, then in fact the entire iteration will preserve that A is tight. And that's due to Guzman, Hrushek, and Tellez. So I haven't told you yet what strongly preserving the tightness of A check is, and I will later. But I hope it's at least clear that essentially morally what this theorem says is that if at each successor stage I preserve that A is tight, then the whole iteration will preserve that A is tight. Now you need a little bit more than just saying that A is tight, but not that much more. And that's sort of the content of this result. And so we kind of knew that, this tightness played well with forcing, and we wanted to know, could we do this for the other almost disjointness numbers? Mm-hmm. And it's still open how to do it for AG and AT, but for AE and AP we can. And that's kind of what I want to show you, is a version of tightness for eventually different families. Okay. I just need a few more definitions in order to define this. So there's a kind of natural immediate way of generalizing tightness for eventually different families. This is sometimes called being omega eventually different. That ended up not being the right notion for us. And then luckily it wasn't called tightness anyway. So we called this tightness, and it sort of involves the combinatorics of trees. So just to be clear, a tree means a sequence of natural numbers which is closed, a set of sequences of natural numbers which is closed downwards under subsequence. And so if I have a tree and I have a node T in my tree, then the cone above T is the set of elements of T that are compatible with it. So I have this tree and I look at my node, and then I just look at everything that sort of extends it plus everything that was down below. That gives me a kind of stem. And so if I have a tree and I have finitely many functions from omega to omega, then we'll say that T is almost covered by these functions f0 through fn minus 1, just in case the union of t is an almost subset of the union of my functions. Now, note that this makes sense because T being a tree, it's a set of sequences. If I take the union, I get a set of pairs. So that's a subset of omega squared. And again, the functions are, again, the union is a set of pairs. So I have, a subset of omega squared being an almost subset of another subset of omega squared. So this kind of, at least it makes sense, right? And so the tree ideal generated by E, which I denote by I of E, it's the set of prune trees. You don't really need prune trees here, but these are the ones we care about. Prune trees are ones where every node has an extension. So there's no sort of finite branches. It's a set of prune trees so that there's some T, and the cone above T is covered by finitely many functions from E. So I can kind of go up to some place in the tree, and above that place, it's sort of almost covered by finitely many things from E. And so dually, the set I of E plus is all of the trees so that no cone can be covered by finitely many elements of E. Now, given a tree and an element of bare space G, we'll say that G densely diagonalizes T. If given any node in my tree, T, I can find a strictly stronger node S, and an element K, and a natural number K, which is in the domain of S, so that S of K and G of K agree. So sort of arbitrarily, so the set of places that G is going to agree with something in my tree is dense, in other words. And another way you can say this is that every node in the tree sits on an infinite branch, which is infinitely often equal to G. So given all of that, what it means to be tight is that anytime I take a countable sequence of trees that are I of E plus, then I can find a single G from E which densely diagonalizes every single one of them simultaneously. And this is similar to the case of MAD families. Tight eventually different families are maximal. It's a strengthening of maximality. And the way to see that is that if I have a tight eventually different family E, and I take any element which is not an E, then either F can be covered by finitely many elements from E, so it's infinitely often equal to one of them, or else the tree of its initial segments, so F restricted to N for each N, is an I of E plus tree. So there's a G, which is going to densely diagonalize it, but this tree is just a single branch. So densely diagonalizing it means you're just infinitely often equal. Okay. Before I move on, are there any questions? Cool. So, sorry, my dog behind me is sleeping and he's running on the couch in his sleep. Why do we use trees? So it's maybe not so totally clear, but it's kind of ends up being the right thing in applications. And so I'm going to give you some examples that show why trees are the right thing to use, but let me kind of sketch the idea first. So like I said before, the motivation for kind of trying to define these tight med families came out of trying to get a similar properness preservation theorem to the one that was proved for tight mad families. And that one, at the sort of key step, uses this idea that actually shows up in a lot of results involving maximal families of infinite subsets of omega, that's called the outer hull. And the kind of setup is like this. Well, suppose you had some sort of, in some sense, maximal set X of infinite subsets of omega that we want to preserve its maximality in a forcing extension in some sense. And so you're in this situation often where you have your forcing notion P, and some condition little p, and I say, well, suppose I had a name x dot for an infinite subset of omega, and then I want to kind of reflect some property of x dot into the ground model. That's what's going to allow me to make an argument. And the way that I do that is we use what's called the outer hull. So x sub p, it's the set of M for which there is some q stronger than p, and q forces that M is an x dot, right? So it's the set of all possible things that might end up in x dot in the extension if I put p in my generic. And so p forces that x dot is a subset of x check p. And so for example, if p was forcing that x dot is outside of some ideal, say, like the ideal generated by a MAD family, then XP will not be in that ideal in the ground model. But this is not really helpful if I'm thinking about functions, because if I have a name for a function, I try to do the same thing, then I'll just get a set of pairs, but it won't be a function, and it's not clear how to work with that. So instead, we can look at the set of finite sequences, so that I've written it differently here than I did on the previous slide, but it amounts to the same thing, so that there is some Q stronger than P forcing that that finite sequence is an initial segment of F dot. And so I look at trying to cover F by these initial segments, and this forms a tree in V, because if some Q forces that S is a subset of F dot, and T is an initial segment of S, then of course the same Q forces that T is an initial segment of F dot. And moreover, similar to how P in the old case was forcing that X dot was a subset of its outer hull, now P is forcing that F dot is a branch through this tree. And this modification ends up being sort of the right one to run a lot of these arguments that had been only looked at in the case of sets. So I'll give some examples, but before I do, I kind of need to take care of something. I need to show you that actually there is a tight MAD family. So like I said, it's not known in ZFC alone if there's a tight MAD family, but it's known under CH. And so similarly, we don't know how to show if there's a tight MED family in ZFC alone, but one exists under MA sigma linked.
Oh God, help us.
One exists under MA sigma linked, and in particular under CH. So I think because of the time, I think I'm actually going to skip this proof. The point is that there's a natural sigma linked poset, which given a maximal eventually different family and a countable sequence of trees will simultaneously add a real, which is eventually different from that family and densely diagonalizes all the trees. And so you can apply the forcing axiom to build up a family of this, a tight family of size continuum. So yeah, I think I want to skip that and just move to the sort of applications. And so these are, I wanted to first present some preservation results that are going to tell me that these tight eventually different families do indeed play nicely with the forcing. So the first is that tight MED families are Cohen preserving, meaning that if I add any number of Cohen reals, then the tight MED family remains maximal. This is not similar to the proof for MAD families, actually, but it uses instead this tree argument, as opposed to the MAD family proof use some stuff about the quantitative ordering. So how does this go? Well, it suffices actually just to add one Cohen real and see what happens. Because every new real in an extension by any number of Cohen reals was actually in the extension by one Cohen real. This is sort of a general fact about Cohen forcing. So if I enumerate Cohen forcing as Pn for n less than omega, and I look at F dot as a name for a new real, a new element of omega to the omega, I need to show you that this new real is going to be infinitely often equal to something in my old tight MED family. So for each n, I look at this tree T sub n comma F dot, which is the set of T initial sequences of natural numbers for which there's some Q stronger than Pn forcing the Q forces that T check is a subset of F dot. All right, so this is exactly this kind of outer hull I was describing. And now there's two cases. Well, so either there's an n so that T sub n comma F dot is in the ideal generated by E, which means that there's a node on the tree, little t, so that above that node, we can almost cover T sub n comma F dot by finitely many functions from E. And if you kind of unwind these definitions, what you get is actually there's a Q which forces that F dot is covered by finitely many elements from E. So that's good. And then the other case is that all of my countably many trees are in I of E plus. And by tightness, then that means that I can find a single G which densely diagonalizes all of them, which means that no matter where I am in the tree, given any Pn, I can find a stronger condition Q, which forces that G check is equal to F dot at any sort of any high K that I like, which means that it's just dense to force that G check is infinitely often equal to F dot. So either way, this F dot can kill the maximality of my type family. And then we also want this strong preservation of properness. So this definition is for type med families, almost the same one is used for type mad families that's in this Guzman, Hushek, Tellez paper. So a proper forcing notion, given a proper forcing notion P and a tight eventually different family E, we say that P strongly preserves the tightness of E if given any sufficiently large theta and a condition little p and a countable model M, elementary submodel of H theta, which contains all of the information. If G and E strongly diagonalizes every element of M intersect my IT of E plus sets, so there is such a G by tightness, because there's only countably many, then I can find an MP generic Q strengthening P, which forces that G densely diagonalizes all of the I of E plus trees in the extension. Okay, so this is, a lot of properness preservation results are kind of phrased in this way. And clearly, if P strongly preserves the tightness of E, then in particular, it forces that E remains tight, because given any condition P and any name for a countable set of trees, I can put it in a countable elementary submodel, and this generic condition Q will force that something from my family densely diagonalizes all of them in the extension. Okay. And then we prove this preservation theorem that's the same as the one for mad families. So suppose I have an E, which is a tight, eventually different family, and I take this countable support iteration of proper forcing notions so that at each successor stage, we strongly preserve the tightness of E check, then in fact, the entire iteration will strongly preserve the tightness of E check. Okay. And this is what we need for applications. Now, let me just say that we can do the same thing for eventually different families of permutations. Basically, everything goes through verbatim. You don't have to change almost anything, which kind of in my mind leads credence to the idea that maybe it's just a fact that AE equals AP. But again, we don't know how to show that. The only difference is that now we want to work with injective trees, which just means that every node is injective. And once you insist that your trees are injective, then you can look at eventually different families of permutations of omega. You define the tree ideal in exactly the same way, and a family is tight just in case there's a single permutation in the family which densely diagonalizes simultaneously all of a given countable family of I of P plus sets. And once you do this, those three theorems I gave you before for tight eventually different families work exactly the same. So under MA sigma link, they exist, they're Cohen indestructible, and we have this properness preservation theorem. So everything I'm going to say kind of applies verbatim to AE and AP, and I'm just going to kind of focus on AE because I think it's the more interesting case. So using this, we were able to compute AE and AP in a number of these kind of well-studied models where they either weren't computed or had only been shown using sort of less constructive means. And now we know that actually the witness is tight, which I think is kind of nice. So theorem, with, like I said, everything I've been saying is joint with Farah. The following posets are all strongly preserve the tightness of all tight maximal eventually different families and all tight maximal eventually different families of permutations. So Sachs forcing, Miller forcing, Miller partition forcing, which is a kind of canonical forcing which increases AT while keeping sort of everything else small. And we didn't know the values of AE and AP in this model, and now we do. We know that they're equal to LF1. Infinitely often equal forcing E, which is a kind of canonical forcing for increasing the uniformity of the null ideal. And this forcing that was introduced by Shalala called QI and as the successor step in his proof that you can have the independence number less than the ultrafilter number. And so again, we didn't know what the value of AE or AP were in this model, and now we can compute them. So using the properness preservation theorem, we can now just apply them to these kind of standard models. And we know now that in each case, we have that AE equals AP equals LF1. And we get these kind of nice cardinal characteristic inequalities. So in the Miller model, we have that D and AT are continuum, while the other these three A numbers are small, and actually AG as well. In this Miller partition model, everything, including the cofinality of the null ideal, which is to say all of the cardinals in the Chacon diagram, remain small except for AT. In this infinitely often equal forcing model, the uniformity of the null ideal and the cofinality of the null ideal become continuum, while everything else, including U, remains small. And finally, we can make U big while keeping everything else small in this QI model. So this was kind of nice. And let me just note that in the case of the Miller model, AE and AP were known to be LF1 by Casterans and Zhang. They proved it using these parameterized diamond principles. And it was unknown in the other models. So we give a kind of very different proof of it for the Miller model and then new facts for the other ones. And let me just note that it was actually known that P equals AT less than AE equals AP. This actually holds in the random model. And it's also not hard to build up a model where D is less than these three almost disjointness numbers. So as a result, we actually get that if I look at any LF1, LF2 valued assignment of AE, AP, D, and AT, which respects the ZFC fact that D is less than or equal to AT, and AE equals AP is consistent, then that assignment will itself be consistent. So we get a sort of nice flexibility there. Okay. How am I doing on time? I'm not sure because I know we started a little late. What time do we go to now these days?
You don't have to worry about the time. I mean, it's just 2:45 now.
Sure.
Like usually we go for 1.5 hours, up to 1.5 hours or something like that. But yeah, it's I think you don't have to worry.
Okay, cool. All right, so I want to just sort of briefly sketch the idea of how we know that Miller forcing strongly preserves the tightness of eventually different families. Because it gives another example of why these combinatorics on trees end up being kind of useful. So recall that Miller forcing is the set of trees so that if I have any node, I can go to a bigger one which has infinitely many successors. And usually the way we actually just think about this is that every node has one successor, infinitely many, because that forms a dense subset of the poset. And any node with infinitely many successors is called a splitting node. And so we say for a natural number n, we say an n splitting node if it has n minus 1 splitting nodes below it. And we do these kind of fusion arguments where we get stronger and stronger conditions, but we never, after the nth stage, change the n splitting nodes. And this will allow us to kind of build a much stronger condition. This is a standard technique. And so I want to show that Miller forcing strongly preserves the tightness of a fixed eventually different family. So remember what that means. It means that if I take a condition in a countable model that contains all the relevant information, and I take a G which densely diagonalizes all of these I of E plus trees in my model, I need to show you that I can find a generic condition which is stronger than P and forces that G densely diagonalizes all of the new trees in the extension. So I enumerate my trees in order type omega as T dot n. Sorry, my names for trees, and I enumerate the dense subsets of Miller forcing in M. And there's some bookkeeping that goes on, but essentially what I want to do is construct a fusion sequence so that we start with this P, and then at stage n, we'll find an n plus first strengthening. So I keep all of my n plus first splitting nodes the same, and then I strengthen above there. And at that same stage, we find sort of a name for the nth element of T dot phi sub 0, then there's some bookkeeping, I don't want to worry about it, but you know, I look at some next element, some next node in this next tree that I want to make sure I'm going to make G equal to at some stage after that. And what I need to do is basically, sorry, the relevant point is here is that if I look at this Pn plus 1 is going to essentially force that at the stage of my bookkeeping, that the tree that I'm dealing with and the node that I'm dealing with, that G will be equal to something which strengthens that node somewhere above the domain of that node, so that we'll sort of in omega many steps make sure to densely diagonalize all of these trees. And if I can do that, then I can take a fusion sequence and I get my generic condition that I wanted. And I don't want to get too bogged down in the details, but we define this fusion sequence recursively. So suppose that I'm up to this stage and I am given this next node, this next name for a tree, T dot sub n, and this next node that I know I need to make sure that I diagonalize above there with my G. And so I can find a strengthening that decides up to that node that I'm dealing with in my bookkeeping. And then I look at this outer hull. I look at all of the ways I might strengthen that node that I decided in such a way that is forced by some condition to end up in the tree. Right, and that sort of outer hull gives me a tree that is in M in the ground model. So I know that G is going to densely diagonalize that tree, which means that I can always find a condition extending the one I'm considering that will force that G is equal to something above my node where I need it to be. And so I can find that condition, and I do that for each splitting node, and I union them together, and I pick names, and this is how I get my generic condition. All right, so I know this is kind of hand waving, but it's a kind of technical argument, but I wanted to just focus on this one section here, that I can always kind of, you know, look at the possible initial segments of something I'm building, and I get this tree. And that's really what this sort of idea is here that we're using. Okay. Questions? Cool. All right, so that was the sort of, you know, the combinatorial question part. And now I want to talk about this definability stuff. And I want to talk about these pi11 witnesses that I mentioned that Arnie Miller proved there's a pi11 MAD family in L. And in fact, he proved a lot more than that. And now we know even more. So the kind of basic question, you know, that I want to ask about is, you know, what are the possible definitional complexities of a type med family? And I think this question is kind of interesting on its own, but it becomes particularly interesting in the context of forcing indestructibility, which has become a sort of a topic in the literature people have been looking at a lot, because we know that tight med families are going to be sort of robust with respect to forcing, which means that if we can find a sort of nicely definable one in L, then maybe I can force over L and I'll still have a nicely definable one, but now it'll be sort of an intermediate size, so smaller than the continuum, but uncountable. And this, you know, we can sort of look at optimal complexities for various sizes and things. So what was already known is that there's a pi11 maximal eventually different family in L, which is Cohen indestructible. So that was proved by Fischer, Schroeder, and Turnquist. And then separately in a different paper, Fischer and Schroeder proved that there's a pi11 maximal eventually different family, which is Sachs indestructible. But in fact, what we show is that there's a pi11 tight eventually different family in L. So this one is simultaneously Sachs indestructible and Cohen indestructible. And in fact, it's indestructible for all kinds of other forcings as well, and weaving these forcings together and all kinds of, you know, more flexible things, so we can sort of build whatever we want and keep a co-analytic witness. And this co-analytic witness is optimal. It's not immediately clear why it's optimal, because as I said at the beginning of the talk, there is a Borel maximal eventually different family, but this tight one will be optimal in the sense that, first of all, in a model where CH fails, having an aleph one sized object, the optimal complexity is pi11, because every uncountable analytic set contains a perfect set. And then it's optimal in I think a more interesting sense. So if I actually take any analytic maximal eventually different family E, then that maximality is going to be killed by any forcing notion which adds a real, any real at all. So having a pi11 tight maximal eventually different family will be optimal for any kind of forcing indestructible maximal eventually different family. So why is this proposition true? Well, being analytic tells you that, first of all, you can apply Schoenfeld absoluteness to say that if I reinterpret my analytic set in the extension, it still has to consist of pairwise eventually different elements. And being analytic tells me that since it's uncountable, it's going to contain a perfect set. And since it contains a perfect set, we actually get a continuous injection of Cantor space into this eventually different family. And so if I do some forcing where I add a real and I look at the extension, I can reinterpret this whole situation there. So I mean, I have a code for the continuous function, and I have a code for Cantor space, and I have a code for E. And I look at that whole situation there, and I look at where F sends this new real. So that's going to be in the reinterpretation of my eventually different family, which is still eventually different by Schoenfeld absoluteness. So this F of X is eventually different from all of the ground model elements of E, which means that we killed the maximality of E. So the best that we can hope for is a pi11 witness to tight maximal eventually different families, and this is actually possible. So theorem, if V equals L, then there's a pi11 tight eventually different family of functions and a pi11 tight eventually different family of permutations. And moreover, if we work over L as our ground model, then all of the cardinal characteristic inequalities I gave you before, and in fact all of those models that I discussed, they hold with this AE equals AP equals LF1 witnessed by a co-analytic set. So the sort of optimal set, both for its cardinality and for the sort of combinatorial properties that it has. And just as a remark, this is not hard once you know this proof and even before, but I don't know if it had been noticed before, you also have a co-analytic tight MAD family by essentially the same proof. So how does this proof go? So this proof comes out of a kind of general strategy that was developed by Arnie Miller in this really beautiful paper from the 80s. I think it's called Infinite Combinatorics and Definability, where he proves a whole lot of results, but some of them have to do with co-analytic witnesses in L. And he shows that there's a co-analytic MAD family and a co-analytic maximal independent family and a co-analytic Hamel base and all kinds of different things. And the idea behind how this works is as follows. So I'm going to kind of sketch it for tight eventually different families, because that's obviously the case I'm considering, but it works kind of just as well for all of these different types of maximal sets, or most of them. There are some that it doesn't, and those are the kind of interesting ones. So what's the kind of naive thing if V is L and I want to build a tight maximal eventually different family? Well, I might try to do it by recursion, where at stage alpha, I let T alpha be the sort of L least. You know, remember L has this global definable well order, so I can look at the L least countable sequence of trees that are positive for the eventually different family I've built up so far. And then F alpha will be the L least element of omega to the omega, which is eventually different from everything I had before and also densely diagonalizes every element of T alpha. All right, so I just look at the sort of least place that I could go wrong, and I pick the least thing that's going to prevent that. This is exactly, for those of you who know, how you prove, for example, that diamond holds in L. And so it's a kind of standard condensation argument using similar to the one for diamond to show that the family is maximal, because if it weren't, you would have a least witness, and you can stick everything into a little elementary submodel, and you can collapse it down, and now everything lives in some countable L alpha. And what you'll basically get is that least witness had to have been dealt with at this earlier stage, and that's a contradiction. But what's the complexity of this set? So in fact, the way that I just described it, the complexity is pi12. Why is that true? Well, a function is in this family E if and only if, so I've kind of written it informally here, and then I'll tease it apart for you. For every L gamma, either F is not an L gamma, or if I go up a little bit further, maybe to L gamma plus omega, then that model thinks that F is in E. And by thinks that F is in E, I mean that, you know, this sigma 1 definition that I gave of this family E, right? I wrote down a definition in L of this family, that this little model thinks that holds. And the for all L gamma really means that for every E, sorry, subset of omega squared that codes an extensional well-founded relation, if I look at it's sort of how it's isomorphic to some L gamma for gamma less than omega 1. So what I'm really saying here is that for every E, which codes an extensional well-founded relation, so that this corresponding model here satisfies a certain theory, B equals L, right? This will be the, you know, level Mostovsky collapse to some L gamma. So either it's not well-founded, so either this sigma 1 fact holds, it's not well-founded, or F is not in the model. Now I wrote it here. Being membership is pi 1 in the codes. So either this sigma 1 fact fails, or this sigma, sorry, holds, or this sigma 1 fact holds, or L gamma plus omega. So if I go up a little further, just to give myself some space, we'll think this thing, and it will be right about it because of the way I constructed my family. And satisfaction is arithmetic in the code for this model, because now I'm just sort of quantifying over the elements of the model. All right, so I have sort of for all, and then exists, the exists that I'm hiding down here, and then arithmetic. So that gives me a pi 1 set. And now how do I strip it down to a pi 1 set? Well, suppose that, you know, thinking kind of broadly, I had some way of coding into each F alpha, you know, at stage alpha, some sufficiently large gamma, so that once I had F alpha, I just had to pull out gamma, and then I could say, oh, well, F alpha is going to be an L gamma, right? And then I don't have to say for all L gamma and blah, 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 blah. I already know where the witness is going to be if there is one at all. If I could do that, then I would just have to say that F alpha codes this well-founded transitive relation, and that transitive relation that I pulled out of F alpha thinks this arithmetic fact. So I have arithmetic, pi 1 arithmetic, and hence I would have a pi 1 set. And this is exactly Miller's idea. And so every time you prove something like this boils down to a kind of coding lemma. And so for us, this coding lemma was that as follows. So for a technical reason that I'll show you on the next slide, we needed in our eventually different family to have each constant function. So I denote by Cn the constant function with value n. Of course, those are all eventually different from each other. In fact, they're completely different. And they also cover omega squared collectively. It ends up being important. And now suppose I had some countable E0 eventually different family, which has all of my Cn's. And I take some countable set of trees in IT of E0 plus. If I can take an what the lemma really says is that I'm in this situation, and given any real at all, arbitrary z, I can find a function which is eventually different from everything in that countable family, densely diagonalizes every tree, and computes in the sense of Turing computation z. And moreover, if I give you E0, my sequence of trees in z, then you can compute f. And so this z, this arbitrary z we can code into the construction is exactly what we're going to need to sort of run this top argument. So I didn't include a proof of this. It's, you know, it's not so hard, but it's just a kind of sitting down and writing out what you need to sort of densely diagonalize a set of trees while being eventually different from something. And you use the CNs to basically say, you know, I know that I want my f to eventually not to have only finitely many times that it is equal to each n, but I can choose to have that be either even or odd. And using that even odd freedom, I can code z. Okay, so given that, we can define sort of again recursively in L this tight med family, the same idea, but now using my coding lemma to strip back one quantifier. So for each finite n, we'll let fn be this constant function. And then at each infinite countable stage alpha, suppose I've constructed f of c for each xc less than alpha. And I take the L least countable sequence of trees that are positive for my eventually different family. And then I construct f alpha as in the coding lemma. And what am I going to code into f alpha? Well, I'm going to code the relation of some L of L alpha. Okay, so I have this sort of copy of L alpha itself that's coded into f. Now f won't be in L alpha, but this definition still is this kind of robust, you know, sigma 1 definition in the sense of L. So it's going to live in at most L alpha plus omega. And there f will have to be in there because it's the alpha thing in this sequence. That it has a nice definition that is kind of absolute between these L alphas. And so that gives me this omega 1 sequence of eventually different functions. Collectively, that's going to form a tight maximal eventually different family. The tightness is this condensation argument. And then to see that it's pi 1, 1, observe that f will be in E omega 1, just in case f computes basically a extensional well-founded relation, which is some L gamma, or isomorphic to some L gamma. So that's a pi 1, 1 thing to say. And from that L gamma, I can, in a Borel way, construct L gamma plus omega. And L gamma plus omega will think this arithmetic fact. So that's how I strip off the quantifier. That's how all of these arguments work. And that gives me a co-analytic tight med family, which then I can iterate over L with to have a co-analytic tight med family in all of these kind of standard models. So the optimal complexity. And so let me just say that kind of a similar coding technique like this works for tight, eventually different sets of permutations, and it also works for tight MAD families. So we can have pi 1, 1 witnesses to all of those in the models discussed. And then it was actually previously known that, moreover, there's a pi 1, 1 maximal independent family. If you know what that is, I haven't talked about it, but it's another one of these kind of maximal sets that can be preserved by a nice family of forcing notions. So that was shown by Brenla, Fisher, and Komsky. And Jonas and Schillen also proved there's a pi 1, 1 ultra filter base for a p point in L, and countable support iterations of proper forcings, which preserve p points. The whole thing will preserve the p point. So what we actually get is kind of, you know, in these models, for all of the kind of extremal sets whose associated cardinal characteristics are L of 1, they can have pi 1, 1 witnesses, kind of all at the same time, which I think is kind of nice. So we get this kind of optimal complexity for all of the Aleph 1 size cardinal characteristics. And that's everything I wanted to say. Thank you so much. This is the paper. It's currently under review. We put on the archive, I think, a couple weeks ago. And thank you so much.
Thank you. It was very nice. Are there any questions for Corey?
Yes, can I ask one question? I think
Yes.
Turnquist proved that if there's a sigma 1, 2 MAD family, there's a pi 1, 1 MAD family.
Yes.
And that gives you a much easier proof than Miller's, that if E equals L, there's a pi 1, 1 MAD family. I was wondering whether there's a similar results for these different notions of maximal.
Right, Turnquist proved that there's a sigma 1, 2 MAD family, there's a pi 1, 1 MAD family, and
if E equals L, getting sigma 1, 2 is dead easy. So
right, exactly. So for maximal eventually different families and for, I believe, maximal independent families, the same holds, that if you have a sigma 1, 2, 1, then you get a pi 1, 1, 1.
yeah.
I don't know how to show that tightness would get preserved in this argument. So I don't know if having a tight sigma 1, 2 gives you a tight pi 1, 1. It definitely gives you a pi 1, 1, 1, but I don't know if it's tight. So, and then the kind of interesting one that is open is we don't know if a sigma 1, 2 maximal cofinatory group gives you a pi 1, 1 maximal cofinatory group, because groups are harder.
Oh,
But yes, you're right. Definitely Turnquist's argument is simpler than Miller's because you don't have to build the pi11 thing directly.
so could you say what is the open question again?
So for a maximal cofinatory group, so a group of permutations, so a subgroup of the permutations of omega, which are pairwise eventually different, but they form a group. So, their compositions are eventually different from each other and blah, blah, blah. Whether having a sigma 1, 2, one of those gives you a pi11, one of those.
Thank you.
Okay, great. Any further questions?
Yes, I have a question way back near the beginning.
Yes.
You had a result that if you have a tight med family and you had a colon real, it's still maximal.
Yes.
Any chance that it might still be tight?
Yeah, it is. It's the same proof. It's just a lot more to write down. So I thought it would be easier to show, to just give what I said, but you're exactly right. Yeah, so it's hard to imagine how something could be still eventually different, still maximal, but not tight, but that would be amazing. But the same proof, you just, instead of having a name for a real, you have a name for a sequence of countable many trees, and then you have sort of countable many countable sets, and you have to work with all of them, but the same idea essentially holds. The point is that the outer hull of a tree is a tree, so it kind of goes through.
Thanks. In particular, that means you could mix in Cohen forcing with all these other things that you're iterating.
Yes, correct. Of course, you need to do countable support in that case, but yes, you can.
Well, yeah, okay.
Well,
Thanks.
actually, no, sorry. No, sorry. I don't know, because the properness result is strong preservation of tightness.
Oh, yes.
And that's probably true, but it's not immediately obvious to me, to be honest. So that's probably true, but I don't know, actually. So I don't want to, let me take that back.
Okay, thank you.
Yeah, thank you.
Okay, any further questions? Okay, everybody seems to be satisfied. Well, thanks again for the very nice talk, Corey.
Yeah, thank you. Thanks so much for having me. It's nice to see everybody.
Just a second. Wait a second. Oh yeah, here I stop recording.